Welcome to the next video on mathematical logic, discussing propositional logic and this time talking about derivations. So derivations are very, very similar to what we've already been talking about with induction, and where induction basically traced out the sequence of applications of formation rules to get bigger and bigger sets. Derivations are kind of like doing the same thing except tracing out a path of taking, applying formation rules to construct a particular element rather than an entire set, something like that. Anyway, so to be more sort of clear about this, let's just jump right into a derivation of the number 3. And the system that we're going to do this derivation in is the same one that we discussed last time, where the basis set is the set of just the number 0, and the set of formation rules is the set of f, where f is the +1 function. And what I've written here is, a derivation of the number 3. So the idea of a derivation, it is a list of elements, all of them in the closure of this inductive system, and it has to be subject to certain rules, namely, at any point, anywhere in a derivation, you are always free to write down an element of the basis set. Then, at any coordinate, you are also free to write down the result of applying one of your formation rules to an earlier element in the list. So, the way that works in this particular example, in the very first coordinate, I really can't do anything other than write down 0 because I have no earlier element, so I can't use that part of the definition. And so I only have one element in the basis set, 0, so that's pretty much all I can write down. In the next coordinate, I can now apply my only formation rule to the only earlier element, and that gets me the number 1. Then I can apply the formation rule to 1 and get 2, and then I can apply the formation rule to 2 and get 3. And there's the derivation of 3. This is the most efficient derivation of 3, but I do want to emphasize that technically, silly, inefficient derivations like this one on the slide are also technically, they qualify as derivations of elements, right? So in this, just to explain it a bit, I write down 0 because I'm free to, it's in the basis set. I write down 0 again. I am free to. You write at any point, you can always write down an element of the basis set. Then for the number 1, I construct it as an application of a formation rule to an earlier element. And technically, it doesn't matter which one, right? I have a choice. Could I view this as applying it to the first 0 or the second 0? Doesn't matter. Either way, I am justified in writing a 1 at that point. After that, I can write 0 again if I want to, because again, at any point, you can write down an element of the basis set. At this point, I get sort of tired of doing this nonsense, and so I just go ahead and derive 1 and derive 2 and derive 3. But that is an inefficient, but still technically is a derivation. Okay, so let's discuss another example. And this one will again be based on an inductive system that we discussed in the previous video, which is the example of full binary trees. So in that example, we said that our basis set, x0, was an infinite set from n1 to n infinity, and our formation rule was just a single formation rule, which we can call f, and f if you give it any two trees, constructs a new node, just out of some laziness, I'll just call that new. You can see the details in the previous video. And makes T1 the left subtree and T2 the right subtree. And so in this system, I'd like to find a derivation of this tree. So to get started, we have to, right, we're effectively going to want to apply f to this node and this node. So in order to make that all formally correct when writing a derivation, we have to start our derivation with elements of the basis set. So we construct n1, which we put it there so that it will be ready for us to apply the function f to when we are ready to do that. But we also need n2. And now, because I have these two elements earlier in my derivation, I am free to make the next element f of n1, n2. And that, right, this final element just is the tree that we were attempting to construct. So that's it, right? That's the derivation of this particular tree. This doesn't line up with exactly what I wrote in the slide. I think I had a mistake when I wrote the slide, but in any case, right, what's on the board is correct. This is a derivation of that tree. Let's now state this a little bit more formally and say that a derivation in an inductive system is a sequence of elements x1 through xn. Each one is an element of the inductive closure x bar, and they must satisfy the following condition, that if xi is in the sequence, then it is, and in the description here, I'm missing the caveat, xi could be either in the basis set or it is formed by some formation rule using earlier elements, right? So that, and there's an even more formally correct definition of this in the textbook, so I won't bother reiterating that. So I just want to give an indication of where this is going and why I think we're talking about this at this particular moment. This is going to give us sort of the tools that we'll use to talk about proofs in propositional and other kinds of logic, because after all, a proof is a sequence of sentences, basically. And we will choose special derivation rules. Now, we've already seen that we can build, right, like by having certain formation rules, we can build up the set of all sentences. Clearly, that's not what we're going to be doing when we talk about proofs, because then, basically any sort of construction of any sentence would be a proof of the sentence. That's not what we want, right? So we're going to restrict our formation rules even further, right? So we don't want formation rules powerful enough to derive every possible sentence. Rather, we want formation rules powerful enough just to sort of proceed to logical consequences, right? So we'll have a new set of derivation rules when we get to that point, which allow each new sentence to only appear if it follows logically from previous sentences. So that'll be a part of our use of these formation rules. Finally, I want to note that the textbook discusses a few things that I'm not going to get into right now because I just sort of suspect that I won't, rely on them very heavily in the future. Talks about countability, so sort of determining the cardinality of the inductive closure of a set. And, basically just the idea is that if your basis set is countable and your collection of formation rules is countable, then the inductive closure of that system is going to be countable. For one thing, maybe I'll just give like a quick, a sort of quick proof of that. Not quite as rigorous as what's in the book, but I mean, if we take it for granted that a countable union of countable sets is always countable, well then if your basis set is countable and you have a countable collection of formation rules, then you can basically express x1 as a countable union of a countable collection of sets, right? Basically unioning a set for each formation rule. So x1 becomes countable based on that idea, and then x2 is countable, and x3 is countable, and so on. Again, every step you're taking a countable union of countable sets. And then if you write the inductive closure is the union of all of these sets together, well, that's another countable union of countable sets, and therefore is countable. So anyway, I'm not going to write up that's my quick version of that topic. And then there's also this idea of subsystems. I'm not going to talk about that in detail. It's fairly straightforward. A subsystem of an inductive system is you just take some subset of the basis set and some subset of the formation rules, and that gets you a subsystem. If I find that I need to explain or talk about these details in any sort of elaboration later on, if it becomes important, I'll do it then.